Problem 189, rotate array. In this problem, we are given an array, and we also have a number k. We have to shift this array to the right by k steps, and we have to do so cyclically. Cyclically obviously means that the array can be imagined as to be on a circle. So any element that falls off at the bottom should reappear at the beginning of the array. The first approach I'm going to try will involve 3 rotations of different segments of the array. So we're going to do 3 rotations of parts of the array. Okay. So think about the following. So after the shift has happened, after we shift the array by k steps, some element is going to end up at the end of the array. Let's assume this is the element which will end up at the end of the array. Now, instead of moving it to the end of the array, I am going to temporarily move it to the beginning by rotating this segment of the array. And this will be our first rotation. So 5, instead of going to its final destination directly, it will temporarily end up in the exactly opposite position in the beginning of the array. Now, the next rotation, our second rotation, will involve the rest of the elements. So this will be the second rotation. Also, consider this element right here. Now, 6 directly follows 5. And if you think where 6 should finally end up after everything is completed. Now, because 6 follows 5, and 5 is going to be in the end, finally, eventually, well, obviously 6 is going to be in the beginning. Now, that gives us probably the idea how to complete the final step. If we just rotate the entire array now, and that will be our third rotation, then we should get exactly what we want. And to see why this will be the case, you can observe 2 things. The first thing is that after these 3 rotations, the order of the elements will be exactly as it was in the beginning. So, and what I mean by this is cyclical order. If you think about these elements to be located on the circle, then the order of these elements would be exactly the same. Because notice that we've rotated 2 independent segments. First and second rotation, we rotated completely independent segments, and then we rotated the entire array. So these segments both will be in the right order, in the original order. Segment 1 and segment 2 will be both in the original order. But now, if you think about 5 will be, so that was our first tick, that the order of the elements will be correct. Now the second tick is that because 5 will finally end up in the correct place after the third rotation, that means this entire segment will be in the correct location. And same for this. I mean, obviously, you don't even have to check anything else now, because this segment has nowhere else to go other than in its right place, because its order is correct. Therefore, you can see that with these 3 rotations, we will get exactly what we need. So we will be shifting our entire array by k elements, k steps to the right. Let's try to implement this now. So first of all, I think it's wise to write a small procedure which will rotate part of an array. So function rotate, and it will take some array, which will be any elements, an array of anything, and then from, let's say, default value 0 and 2 would be array length -1. So we're going to rotate the entire array. If you don't, if you skip these parameters, that means we will rotate from element index 0 to the last element. Now, how are we going to rotate it? Let's think about this for a second. Let's say we are rotating this part of an array. So here the index of this is from, right? This is from, and this is to. What's going to happen is we will have a number of swaps to perform. This one swap, another swap, another swap, and then optionally you can perform the swap in place if you want to, if the number of elements is odd. Now let's see how many swaps do we have to perform. Now if you think about it, the number of elements is 2 minus from and plus 1. That's the number of elements in the segment that we're rotating. If you divide this by 2, and let's take the floor, that will be the number of rotations, the number of swaps we need to do. Because we're taking the floor, that means we are never going to be swapping this in place. If we were to take the ceiling, then we would swap this, rotate this element in place as well, but we don't need that. So this will be the number of swaps. So I could do swaps starting from 1 all the way to whatever this number is, yeah? However, if I wanted to do this from 0 to, so number of, let's say I wanted 0-based number of swaps, and I'm just to let you know what I'm going to be doing, I'm going to be using this number as an offset. So this will be an offset, yeah? So offset 0, offset 1, etc. So the largest offset will be -1 because we're going to do 0-based. Now this -1, it's easy to see that, to actually accomplish this -1, we can, let me just explain. So this -1 here means -2 here, right? So we can get rid of this -1, and basically what will happen is this. So this is the largest offset starting from 0. If we do this sort of thing, offset 0 will give us this swap, offset 1 will give us this swap, and then the last number, this one, will give us this swap right here. Okay, so we should be able to write this, I think. So what this is doing here is basically divide this by 2 and take the floor. That's what this binary shift will do. So our offset would be from, basically, I'm going from 0 to this number, but I'm going into the opposite direction, which is fine. Instead of k running from 0 to this, k will be running from this to 0. And the reason I'm doing this, I don't want to do this, calculating this every time this condition is being checked. And then minus k, because we are going, We're decrementing k every time. Okay. So create two variables, I and j. These are indices that we're going to swap. So these will be, I will be from plus k, and j will be 2 minus k. And that's precisely what we want, as we discussed here. So from plus offset and 2 minus offset. And now we're just going to swap elements, the following elements, array I and array j. And to swap these, I'm going to just do something. I'm going to use a technique to swap them without using any additional variables. So these three lines, will achieve swapping array I and array j. Okay, this is a binary, this is an XOR, binary XOR, bitwise XOR, sorry, not binary, bitwise XOR. So this thing should rotate a segment of array starting from an index to an inclusive an index. So these are both indices. Right, so now we are kind of ready to write the main part of the function, rotate, main part of the problem. Now, we still need a little bit of thinking to do here. Let me clear up the board again. So remember, we have to do 3 rotations. But the main idea here is the main thing that we need to understand, we need to calculate is what is that element which will end up being the last element. That's crucial because that is the point which will define our 3 rotations, if you remember, right? These 3 rotations. So we need an index of this element. So we're going to be moving everything k steps to the right, and we have to find an index I, which will end up in the end. Notice that k could be a very large number. So when you move any element k steps to the right, it could end up going around multiple circles around this array and finally come here. So it's not as simple as it initially may sound, but it's not that hard either. So basically, when we take I and we add this number k, however large or small it is, what should happen is we should in some sense end up at the, let's say n is the number of elements in the array. So n is the length. So I plus k should be n minus 1. That would be the index of the last element, right? So n is length. So length is n. However, what if k is very large? So basically what should happen is this should be true modulo n. Right? So if you wrap around any number of times around this array, that would mean that this number, this index, after you add k to I, you should get some number that is n minus 1 modulo n. Now, we can easily guess what I should be from here. I would be n minus 1 minus k modulo n. So this is k. Basically, now the problem with this is we're going to use, to calculate the remainder, in JavaScript we're going to use these percentage operator. And percentage operator may return a negative value sometimes when this number is negative. So we have to take care of that as well. Okay, let's go back to implementation now. All right, let's create that n, which is length of the array. Now, after we do that, we need to calculate I, which will be the index of this element. I is this index, right? So I will be, and as we said, let's remind ourselves, n minus 1 minus k. So n minus 1 minus k, and we need to do this modulo n. However, if suddenly this thing ends up being negative, it's not going to be, let's say, too negative, if I can say so. It's going to be just enough. So if we just add n to it, we're going to end up in the right range. So we could do this. So if for some reason this ends up to be negative, it won't be, it's a remainder in a sense, but a negative remainder. So it's still going to be, its absolute value is going to be less than n. So if we add n, then we're going to end up with a positive remainder. So now we have to do our three reversals or rotations. We call this rotate. We cannot call this. We should call it reverse or something like that. Okay, so we should do now reversing 3 times. So first, we're going to reverse our array from 0 to I, right? And that's exactly what we need. If you remember the first reversal, if this is I, the first reversal will be from 0 to I, exactly this. And we did that. Now the second reversal will be this. So this is our second reversal. Now the problem is these numbers may not exist, which means, say, if k is a multiple of n, if it's multiple of the length of the array, then we're basically not even shifting anything. So it will be 9 which will end up in the final position. So the final element will end up in the final position. So if the final element is I, then there is nothing left to reverse, right? But otherwise, the next reversal would be I plus 1 and to the end of the array, right? So let's go back. The next reversal is reverse nums starting from I plus 1 and to the end. So I can skip the last parameter because, as you remember, it will be automatically the end of the array. Now, question mark here, because if this exists or doesn't exist, we have to think about this one. But the last bit is we just reverse the entire array, if you remember. So we just reverse nums. And again, if I don't give any the rest of the parameters, it will just reverse the entire array. So this is questionable. However, with this particular implementation, it will still work because this reversal won't really do anything. It won't destroy anything because what will happen is from will end up being greater than 2. So from will be greater than 2, and this loop will just won't run. It will instantly, so basically this will give you a negative number and this condition. So if from is greater than 2, then this is at least minus 1. This is at least minus 2, which means when you divide it by 2, it's at least minus 1. And this will also truncate towards minus infinity, this one. this will truncate to minus infinity. When this is truncated to minus infinity, that's a negative number, and this will kick us out of the loop. So nothing will happen. Technically, I don't have to do anything here. But to be quite honest with you, it looks very pretty like this. But maybe we still should protect it. If we later change the implementation of this, we don't want some nonsensical, some sort of command here that will mess things up. So if I plus 1 is less than n, then we can still rotate it. Okay, I think we are ready, unless I've made a mistake. Let's try running this on the pretests. Beautiful. What is it? Left-hand side must be, all right, so unknown, yes. We have to make this into a number, because the technique that I'm using, it's not gonna swap any value. It has to be a numeric value and an integer value. Okay, so we passed these simplistic tests. Try to submit it now. Okay, waiting for the verdict. Do not. Okay, so 4 milliseconds. We've beaten roughly half of the other implementations. Memory is 69, so we've beaten not many, just 8%. Maybe we can improve memory, right? But this will be a completely different solution. For the second solution, I'm going to introduce a number q, which I'm going to define as the greatest common divisor of our number k and the total number of elements in the entire array n. So this number q, defined like this, will play an important role in our solution. Let's say this is q minus 1. So an element with index q minus 1. Now this element will be somewhere inside the array, and the reason is that q cannot be 0. So q minus 1 must be at least 0. I mean, it cannot be negative, because q cannot be 0. It's a factor of k and n, so it can't be 0. It's a positive number. Also, q cannot be greater than n, right? Because it's a GCD of some number and n. It cannot be greater. At the maximum it can be is n. So q minus 1 could be at most this last element with index q minus 1. N minus 1. So q minus 1 is here somewhere, right? Now, think about all of these elements from index 0 to index q minus 1. I'm going to make a couple of claims about these elements. So the first claim will be this. Imagine I choose any element from here, and I make a jump as required, k steps to the right. And potentially then I can make the same jump and potentially wrap around again. Yeah. So maybe wrap around, I don't know, however many times. So k could be quite a large number. So I could wrap around multiple times. But what I'm saying is, I could never touch any of these elements which are different from our chosen starting point. I could never touch any of the other elements. That is my first claim. So I'm never going to touch any of the other elements inside this little group. My second claim will be that this jumping, right, will eventually come to an end, in the sense that I'm going to repeat myself and the repetition will happen the first repetition will happen where I started. Okay, this is the starting point, and I will eventually end up here. That will be my first time when I repeat myself. Okay, let's try to prove these ideas. Now start from the point, let's say we have two indices, I and j, both within this from 0 to q minus 1. Is it possible that at some point we'll end up on j if we started from I? Well, in order for this to happen, the following should be true. So I plus some number of k jumps, right? Let's say we jumped m times. And this should be the same as j, potentially wrapped around a few number of times. So this is wrapping around L times. L is the number of times we wrapped us. Now, because Q is a GCD of K and N, so K and N both have Q as a factor. So this thing and this thing are both multiples of Q, both of these. Now then, if you look, we have that I minus j is, so I minus j is some multiple of Q, right? It's some multiple of Q, but that would only be possible if I equals j. Otherwise, we would have a non-zero number with an absolute value in this range, so less than Q, and it's a multiple of Q. That would be not possible. So the only way this is possible is I minus j is 0. So I and j are exactly the same. Okay, so we proved the first part, that we can never touch any other element other than the starting point inside our little chosen group of elements. Now, so first tick. The second thing we need to prove is that these jumping will eventually is bound to repeat, and the first time you're going to land on the spot you've been before is going to be the spot that you started from. Okay. Now it's easy to see, let's put a small tick here. It's easy to see that you will eventually repeat yourself because you don't have infinite number of elements here. So at some point you're bound to repeat yourself. You have to land on a spot where you've been before. Now, let's say this is the element that you first repeated. So you repeated it. So you repeated it first, which means you had come here before from somewhere. And now you came here again. So that's what that means. So you've repeated it because you had come here before and now you came here again, but you could have only come from one spot. So that spot must have been repeated as well. That means this should be the place where you started. Okay, so we can turn this into a big tick mark. So you will repeat yourself, and the first time you repeat will be the starting place. Okay, which means we have a beginning of an efficient algorithm here, which is the following. So if we consider this segment that we have highlighted from index 0 to q minus 1, we could initiate a successive operations, once from 0, then from 1, then from here. So from all of these elements, we can initiate the following. So you just jump k steps, right? Swap these elements. Then you jump k again somewhere, swap with the previous landing, etc. So you jump again until you end where you started. When you come back, you do one more jump, one more swap, and then this is done. Now I can move to the next starting point. Then do the same for the next starting point, and so on for all starting points in the segment that we've chosen. Okay, so if we get this idea, then we can try to implement this now. Okay, let's get rid of this solution, right? And, well, first we would need to calculate GCD, right? So let's quickly write a GCD, which takes two numbers. And let's use Euclid's algorithm here. So while, let's say, A is positive, we're going to replace, so what I'm going to do is I'm going to pretend A is the smallest one always. So I'm going to replace the largest one with the remainder, with its remainder after division by the smallest one. Okay, so here, look at this thing. So I'm keeping the smallest number. I'm getting rid of B and replacing B with its remainder after the division by I. Right? Now, obviously, I was the smallest, but now I will become the largest. This is why this number is first. And this number goes into into A, because I want A to be the smallest one during the next iteration. So anyway, this would work. I just need to return B. If A is 0, we come out from this, A will be 0, which means B is the answer. Now, what did we say? I just almost forgot. So we're going to take the GCD, right? The first thing we need to take the GCD. So we'll call it Q. Let's take GCD of, and we said K and the length of the array, right? I think that's what we said. Yes. Now we're going to do a small loop, right? So we will do, let's say, the outer loop will be, let starting position be 0, and then the starting position has to go all the way to Q minus 1. Well, sorry. So it should be less than Q, and then plus plus start. Right? Excellent. So now we're going to do this little jumping around and, that sort of stuff. How should we do it? Now, the loop, the inside loop is going to be slightly more complicated. It's not your standard loop. Okay. Let's look at this. This is going to be interesting. So let I be start plus K. So I'm going to save the value at start. So the value that we need, so the value at start, we also need to, obviously start is important. We need to swap this value. We need to take this value and move it to here. So I'm going to start, but potentially this could already wrap around the array. So I need to take, n equals num's length. So we're going to start from here. Then we're going to stop as soon as we finish, or as soon as we reach where we started, right? So until I is not the same as start, we're going to keep doing it. So notice that we're not starting at start. We're starting at a different location. So when we reach start, we could stop. And we just need to, okay, in terms of each, next time we have to do what? So I should be I plus k modulo n, right? That means basically next jump is the same. So we add k and just do the wrapping by, doing modulo n. Okay, but after we are done, so that I don't forget, after we are done, I have to take nums start and assign value to it. So value will be the previous, the value from the previous spot the last spot that we've visited, and we've memorized this value. Initially, it's the starting position. I've memorized it, but we're going to end up in the same place in the start. And val at this point will contain the last position that we visited. So we have to still do this assignment here. But inside the loop, I have to do a swap basically. I'll explain what I'm doing. So val contains the previous value. So I have to swap val and nums I, right? Nums I. Yeah, those two things have to be swapped. And to do that, basically what I will do is I will say value nums I assign nums I value, right? So that will accomplish the swap. Actually, why not keep this as a comment, right? So we're going to swap this. And that seems to be good. That seems okay. I think I can use this time and try to test this. Okay, let's test on the pretests first. Oh, we passed the pretests. Nice. Okay, now remember this. This is the result from our previous submission. So 4 milliseconds and about 70 megabytes of memory. We've beaten only 8% of all of the submissions. Oh, right, sorry, wrong button. I have to press submit. Okay, submitting. Okay, I think that means